this is the second part of your similarity tutorials, and here I'll start off by telling you the basic theorem of proportionality. Very easy and very important as well, especially in this chapter. So what this theorem says is that if you have a triangle like this, say let's call it ABC, and you draw a line in the triangle such that it's parallel to one side and it cuts the other two sides. So we're talking about a line like either like this, or you could even draw it further up in the triangle like this, or you could draw it like this as well. Just pick any one side and draw a line that meets the other two sides and is parallel to the third side. Okay, so let's take in this example, let's just take this line, it's most convenient, it's a straight line. Okay, so here let's name it DE. So what this whole theorem says is that this parallel line, I should draw the parallel signs, divides the other two sides, which is AB and AC, in the same ratios. So say I have, let's take one color over here, let's make it like this. Okay, I need to make it straight, sorry, this is going to take a bit of time. And then I'm going to take another color, say blue over here. I'm going to take this here. So now I have this line over here, it's orange and blue. Orange is AD and DB is blue, you can see over here. So this is a ratio between orange and blue. You can see that the amount of orange upon the amount of blue, no matter how I extend this line, I can stretch this line or make this line shorter, that ratio will remain the same. So I'm taking a copy of this whole line, orange and blue. It's here. Now, just to show you, say if I expand it like this, what you're going to see is that the ratio between orange and blue still remains the same. Blue is still going to be far lesser than orange. If I expand it from this side, you'll see the same thing. That blue is still in that same ratio. Amount of orange upon amount of blue is still, it's a constant, even if you stretch the line. So now what I'm going to do is just rotate this line along AC in the direction that AC is in. It should be somewhere here. And I'm going to place this line right here. And you can see that it's falling short a bit, and it's also not rotated very nicely. So I think this should be good. And I should also extend it so that the blue part meets C. Yeah, that's fine. So you can see over here, I've extended it, I've rotated it. Now what you see is that the orange and blue over here, they meet at point E. That's what this theorem is all about. This ratio over here between orange and blue is equal to this ratio over here. And the condition is that the line that is running across the triangle, which is DE in our example, needs to be parallel to the third side, which it is over here. So amount of orange upon amount of blue, let's take orange first. So orange upon blue, orange upon blue is constant whether you take the side AB or you take the side AC. And you see that they both meet at the points DE, D and E, not DE, and those 2 points form the line DE. So this is the basic theorem of proportionality. It'll come use in your when you are solving the problems, but I'm going to leave it here for now. And the second part of the chapter, which I think is the more important when you talk about similarity in grade 10, is all about maps and models. So before I start that, I'm going to rub all this out. So maps and models, as you know, say you're drawing a map of a country, I'm sure you would have done scales in geography under topo and all that. But obviously, if you're drawing the map of a country like India, you can't draw a map that is actually the full scale size of India. That's going to take kilometers of paper. That's not practical at all. There's no use of that as well. So what you do instead is you scale everything down, and you use a constant. You can't have an India that looks like uh, um, I don't think that's a very accurate drawing. But okay, I'm gonna start this again. So the second part of the similarity chapter is, I think, the more relevant one in grade 10. This is where you deal with maps and models. So first I'm going to start with maps. You can see I have a Indian map over here. So by the way, the source for this is geography.about.com. Just telling you the source. If you want it, you can go there and see it. So when people are drawing these sort of maps, they need to keep some sort of scale. You can't, you can see I've opened the scale dialog over here. You can't have an India map like this, right? It's way thicker than it should be if you look at the proportions of it. So it's just like if you look at India from a satellite, if you draw the map from space and you draw a map on a piece of paper, the shape should resemble, it should be similar. Hence, we're doing it on the chapter similarity. You can't have on the map it being so wide, and in actual it can't, it's way less wider. So you need to maintain that shape, and for that you have something called the K factor, or the scale factor also it's called. So how much you want to scale it depends on how small or how big you want the map to be. Say I want it to be this small, so my scale factor will be that smaller. If I wanted it to be this big, it's a bit too big. Yeah, this is fine. Then I'd have a bigger scale factor. So depending on that, there are a few formulae. I'm going to take this map out. Yeah. So few very basic formulae. Now you always have a scale given in this form, 1:k. This is your factor over here. Scale factor, you could call it whatever. So say it is 1:10. That means that if you had 1 meter on your map, that would actually equal to 10 meters on your actual ground, right? So if you had 1:50,000, that means that if you have 1 centimeter on your map, that would actually equal to 50,000 centimeters on your real ground. So this is all you need to know, and this is always called the K factor. And keep in mind, you need to express it as 1:k. You can't have 2:30,000 and say that 30,000, is the K, the scale factor over here. You need to reduce this over here to 1. So it'll be 1:15,000. So there are a few very basic formulae before I leave you. For maps, you're only talking about length, breadth, and area. You don't have volume over here yet. So length, if you want to find length in the actual figure, which means actual ground. So length actual, I could write, is equal to this k over here, the k that you figure out over here, into the length in the map. Remember that the k in all these formulae is always multiplied by the length in the map, not the length in actual. You're always finding length in actual. This is just something you need to remember. You just have to remember it. Same you could say for breadth as well. If you want to find the actual breadth of the map, you just multiply the k by the breadth on the map. Now if you want to find area, you don't multiply k, but you multiply k square, and you multiply this by the area of the map. So say I have a map of India, its scale is say 1:100, and I want to find out that 1 centimeter square on the map is equal to how much in real. So I just multiply that k, the square of k rather, into the area on the map, and I'll get how much it is in real. So that's it for models. And the same thing is true, sorry, for maps, not for models. Now I'll move on to models. And for models, it's the same thing. Again, you have 1 is to k, but the only thing new over here, again, by the way, if you have uh, k into any side of a model you can have like a 3D model of a building or anything. So if you multiply k by any side of the building, any dimension, to the right side, you'll get the length of the actual side in real. Similarly, if you do k square, say you want to find the surface of the building, you've been given k, and you can easily measure that on the model how much is the surface area of one side of the building. So you could say side area here is again equal to the real area if you actually go to that building and see. And now the newer thing over here is k cube. So keep in mind that models are always three-dimensional. Well, not always, but they can be three-dimensional, while maps will definitely not be three-dimensional. So here you multiply it by volume of the model, or whatever part of the model you're taking. So if you have k, you multiply by side, so the unit will be meter over here. If you're doing k square, then you do meter square. If you're doing k cube, then you do meter cube. And I think the you in these questions, they're normally not they don't add a touch of reality to these questions. So often you'll get that the volume of a ship is like 10 meter cube. I know you'll get answers like that sometimes, which don't really make sense, but I think in this chapter, just stick by whatever answer you get. I know it sounds strange. Your ship can sometimes be as small as a bottle of Coke, but I mean, that's what the chapter is. The main thing the testing is how well you know your volume, your area. And one thing you should definitely do before your exam is go to Google or go to any book which gives this properly. Just search for conversions in volume from meter cube to liter to centimeter cube, all that, because that comes in use a lot. And at the same time, if your volume comes out to be a liter or something, don't compare it to a bottle of water or something. Then you will get confused. Just take it as it is and just trust your answer and you'll get it right. So I'm not going to do sums here. There's not many. They're all based directly on the formulae, and there are lots of proof questions. I can't prove all of them, but definitely, again, like the chapters like circles in trigonometry, where you have lots of these proof questions, we can't do all of them for you. And so only if you have a doubt in any one of those, you can contact us and we'll try and solve it for you as soon as possible. But for now, we're not doing any sums here. Just remember all this, and I think you'll be fine in similarity.